The marathon is special because it is unparalleled in its capacity to capture the collective imagination of a global community of fitness enthusiasts, male and female, elite and recreational, young and old. In 2024, an estimated 2.2 million people finished a marathon across several thousand events worldwide. Major races like the New York City, London, Berlin, Paris, Chicago, Boston and Tokyo marathons regularly drew 50,000 or more finishers, with multiple events setting all-time participation records during the year. Marathon running has become a firmly established global phenomenon, with most major cities hosting an annual marathon that closes large sections of the urban streets to accommodate tens of thousands of runners. From a physiological perspective, the marathon is a particularly intriguing challenge of human performance. The body changes drastically to cope with the cardiovascular, metabolic, neuromuscular, thermoregulatory, and biochemical demands of running 26.2 miles. It is a scenario in which multiple systems operate near their sustainable limits for hours at a time, and in which the runner must continuously regulate effort to avoid going over the edge. At the start of the race, your endocrine system releases a surge of adrenaline, which will increase your heart and respiratory rates. As the race begins, all of your physiological support systems, your musculoskeletal, your cardiovascular, respiratory, digestive, immune, nervous, and endocrine systems will immediately go into overdrive. Your heart will have to pump 3 to 4 times the amount of blood around your body during a marathon than when you are resting. This blood and the oxygen it carries will go to where it is needed, so away from your digestive system and towards your muscles. Those muscles will generate large amounts of heat, 30 to 40 times more than normal, as they repeatedly contract, propelling you forward over the 40,000 steps that you will take during the race. To control your core body temperature, blood will be shunted to the skin surface, and as you sweat, heat will be drawn away from your body. Over the entire course of the marathon, you will lose 3 to 6 liters of sweat, sometimes more in hot or humid environments. You will burn about 100 calories every mile, so that by the time you hit mile 20, your glycogen stores will become low, and provided you haven't been taking on any extra fuel during the race, your main energy source will transition over to fat. Whereas your muscles can store roughly 2,000 calories of glycogen, they have tens of thousands, often close to 100,000 calories in the form of fat. But breaking down fat for energy is much slower than carbohydrate and relies on different biochemical pathways, so the marathon will test those systems too. Late in the race, your body can reach a tipping point. Its ability to resynthesize ATP may no longer be able to keep up with the energetic demands of the race. Over the course of the race, your muscles will have accumulated metabolites due to their repeated strenuous contraction, hydrogen ions, inorganic phosphate, and others, and these contribute to the sensation of heaviness and slowing. Numerous micro tears will have developed within your muscle fibers as they undergo hours of repetitive loading. Your core temperature might rise towards the upper limit of what is safe. Your glycogen reserves could be close to empty, and so you start to slow down. This, in a nutshell, is the peripheral model of fatigue, sometimes referred to as the homeostatic limitation or the catastrophe model. In this model, fatigue during prolonged exercise can be explained by failures or near failures of systems outside of the brain. The cardiovascular system, because of an inability to supply enough oxygenated blood, neuromuscular fatigue or muscle trauma, biomechanical alterations or thermoregulatory strain. Looking at each of these peripheral systems separately, we can begin to piece together how the body works to maintain homeostasis during long-distance running events like the marathon. Failures of the cardiovascular system are based on the premise that the heart is unable to supply sufficient oxygenated blood to the working muscles. This limited supply, along with the capacity of the muscle to use oxygen, which depends on fiber type recruitment and mitochondrial density, may result in greater anaerobic contribution at certain moments. Performance is then inhibited, not by oxygen starvation in a literal sense, it rarely reaches that point in trained athletes, but by a mismatch between oxygen delivery and utilization. Failures of energy supply involve reduced availability of adenosine triphosphate or ATP. The body's main ATP production pathways, phosphocreatine breakdown, anaerobic glycolysis, aerobic metabolism of carbohydrate, and aerobic metabolism of fat, can, during prolonged and intense exercise, struggle to maintain ATP resynthesis at the rate demanded. When this occurs, the ability of muscle fibers to contract with the same force or frequency declines. Neuromuscular fatigue too can occur in a few different ways. Central activation failure posits that fatigue occurs due to a reduction in neural drive from the central nervous system. Neuromuscular propagation failure sees fatigue as the result of reduced responsiveness of the muscle to an electrical impulse, and peripheral failure refers to mechanisms inside the muscle itself, particularly the processes involved in excitation-contraction coupling, regulation of calcium availability, and metabolite-induced interference with contractile function. Regardless of the precise mechanism, the net result is a reduction in the number and firing rate of motor units being activated. This is separate from the muscle trauma model of peripheral fatigue, which is grounded in the structural and biochemical damage that occurs in working muscles during prolonged exercise. This damage alters ionic pump activity and disrupts chemical homeostasis. It may activate pain receptors, which further influence neural drive and contributes to the sensation of fatigue. The thermoregulatory model suggests that fatigue is a result of the body approaching critical temperature thresholds, whether in the core, the muscle, or the skin. As temperature rises, the body increases skin blood flow to dissipate heat. This creates a competition for blood flow between the skin and working muscle and increases cardiovascular strain. Elevated muscle and core temperature also influence central perception of effort through sensory feedback. Finally, the biomechanical model posits that fatigue is governed by the efficiency of movement patterns. As cardiovascular strain rises, as energy availability declines, as neuromuscular control becomes altered, or as muscles become damaged, running biomechanics changes. These alterations may increase oxygen cost, increase mechanical stress, and accelerate fatigue. In all of these models, fatigue is seen as the direct result of a failure of one or more physiological systems, a failure that forces the athlete to slow down. But there is a problem with this model. It cannot easily explain the end spurt that we so often see in both elite and recreational running. Research published back in 2006 analysing the pacing patterns of almost every world record set in the men's 800 metre, mile, 5,000 metre and 10,000 metre races showed that for the three longer distances, after a quick start and a settling period, runners consistently accelerated in the final stages. Even though their muscles were presumably fatigued and their physiological systems were stressed close to capacity, they somehow found the ability to run faster. In all but one of 66 world records in the 5,000 and 10,000 metres dating back to the 1920s, the last kilometre was either the fastest of the race or the second fastest. A similar effect appears in the marathon. In 2014, researchers analysing a dataset of over 9 million marathon finishers found characteristic spikes in finish times just under key thresholds, 3 hours, 4 hours, 5 hours, and so on, suggesting that runners were capable of speeding up late in the race to achieve a goal time, despite widespread fatigue. The cruel metabolic demands of the marathon, which inevitably deplete glycogen stores and elevate perceived exertion, mean that most people slow substantially in the final miles, but with the right incentive, some are able to speed up. Only the brain can respond to abstract incentives like breaking 4 hours for an arbitrary distance like 26.2 miles. This idea that it is actually the brain that plays a key role in determining performance through a process of anticipatory regulation was first proposed in a 1998 paper by Professor Tim Noakes. In that paper, Noakes argued that the brain acts as a central governor, regulating performance in order to balance all of the body's physiological systems. In this model, fatigue or the slowing of pace is not the result of a catastrophic physiological failure, but rather the result of regulation that occurs before such failures can actually develop. In contrast to the peripheral model of fatigue, the theory of anticipatory regulation posits that slowing down occurs in order to prevent true failures of the peripheral systems I talked about earlier, rather than in response to them. In other words, performance is not regulated, not determined by peripheral physiology. The central governor, which was later renamed the process of anticipatory regulation, appears to develop over time. A 2012 study of more than 100 school children between the ages of 5 and 14 completing a battery of cognitive and physical tests provides a useful illustration of this. Younger children tended to adopt an unfettered sprint and then hang on for dear life approach before steadily fading as fatigue accumulated. In contrast, older children adopted the familiar U-shaped pacing profile that we see in adult endurance athletes and world record holders. A fast start, a period of controlled pacing, and then a fast finish. It seems that sometime around the age of 11 or 12, the brain has already learned to anticipate future energetic and physiological demands and to hold something in reserve. So within this anticipatory regulation model, there are inputs and outputs. The inputs are provided primarily by the peripheral systems, and they are communicated to the brain via afferent feedback pathways. Some of the most important of these signals originate in the working muscles themselves via specialized sensory nerves, often referred to as group 3 and group 4 muscle afferents, which are sensitive to mechanical strain, temperature, and the chemical byproducts of metabolism. Alongside these signals, the brain is continuously receiving information such as how hot is it, how sore are my muscles after yesterday's session, how much energy is available, what is the pH of the tissues, how hard is the heart working. Taken together, these signals effectively answer a more fundamental question. Is it safe and is it sustainable to keep going at this pace? The brain integrates all of this incoming information and evaluates it in the context of the exercise bout. Now, this evaluation is not based solely on physiology in isolation. It also incorporates a conscious awareness of how far the athlete has gone, how far they still have to go, and a range of other contextual factors or moderators. These moderators include prior experience, expectations, motivation, emotional state, and the perceived importance of the task. The same physiological state can therefore result in very different pacing decisions depending on whether the runner is at mile 5 or mile 25, training alone or racing, chasing a personal best, or simply trying to finish. The output of this process is the efferent response, the activation or inhibition of skeletal muscle. The efferent response determines the force output of the muscles and ultimately the pacing strategy adopted by the runner, including whether an end spurt is possible. Importantly, the brain itself also acts as an input within this system. Different brain regions communicate with one another before and during exercise, shaping how physiological signals are interpreted and acted upon. For example, the hippocampus, embedded deep within the temporal lobe and central to learning and memory, integrates previous experiences of training and racing and social environmental cues and conscious goals with information from motor and premotor areas in the frontal lobe. In the anticipatory regulation model, the end spurt is therefore the result of an increase in muscle activation that is permitted and orchestrated by the brain in response to this changing balance of inputs during exercise. As the finish line approaches, the remaining distance shortens and the potential physiological consequences of pushing harder are no longer deemed harmful or limiting. The reserve can then quite literally be released. But does this not mean that fatigue or the limits of performance are simply all in the mind? Mental fortitude and willpower are important, but they never override physiology. If oxygen delivery were truly insufficient, if core body temperature rose above safe limits, approaching or exceeding 41 degrees Celsius, or if severe metabolic disturbance occurred within the muscle, the consequences would be quite dangerous. But these occurrences are pretty rare in sporting contexts. They do happen, but they're rare. So, within this framework, fatigue can be understood not as a single failure point, but as a sensation, often subconscious, that reflects the brain's ongoing integration of physiological strain, sensory feedback, and the perceived demands of the task. It is both protective and performance limiting, shaped by biology but interpreted through experience and context. The practical manifestation of this for the runner approaching the end of a marathon is that there are multiple cues, signals, experiences, and physiological variables that make it possible to slow in the middle stages of the race and then speed up again at the end while still producing a pacing strategy or profile that is in retrospect optimal. Ultimately, the biology of fatigue during endurance running is incredibly complex, so complex that measurement might even be considered impossible. How could we possibly study fatigue when it is the product of so many interacting and complex systems? Could there be a single mechanism or system that integrates information about body temperature, oxygen availability, fuel status, muscle damage, and cardiovascular strain, while also responding to subtler influences such as motivation, mood, expectations, and even how much you slept the night before? The answer is yes. It's called Borg's Rating of Perceived Exertion, or RPE, named for Swedish psychologist Gunnar Borg, who pioneered its use in the 1960s. Though there are many variations, Borg's original scale runs from 6, no effort at all, to 20, maximal. A score of 13 or 14 corresponds to an effort you'd call somewhat hard, and for most people this aligns with a heart rate of around 130 to 140 beats per minute. But Borg viewed the effort scale as much more than a proxy for heart rate. Perceived exertion is the single best indicator of the degree of physical strain, he wrote, because it incorporates information from muscles and joints, the cardiovascular and respiratory systems, the central nervous system, and the emotional and cognitive state of the athlete. RPE rises gradually during a marathon, not only as your temperature increases or your glycogen stores decline, but also as you accumulate muscle damage, as afferent feedback increases, and as your brain evaluates the remaining distance and your capacity to finish it. RPE doesn't wait for a catastrophe, it anticipates it. In many ways then, RPE is the final arbiter. If the effort feels too hard, you slow. If it feels manageable, you might speed up. That may sound obvious, but it has profound implications. You can change perception of effort through psychological and cognitive strategies, through better pacing, through better training, and through experience. Positive self-talk, for example, can reduce perceived effort and increase endurance capacity, even though underlying muscle physiology remains unchanged. Similarly, mental fatigue increases RPE and reduces endurance performance without altering physical capabilities. And yet, despite the remarkable capacity of the brain to regulate effort, to anticipate future demands, and to protect the body from harm, true physiological failures can still occur. Under extreme conditions, runners may experience exertional heat illness, including heat exhaustion, or in severe cases, heat stroke. In susceptible individuals, serious cardiovascular events such as arrhythmias or ischemia may occur. Severe disturbances in fluid or electrolyte balance can develop. And perhaps most commonly of all, the musculoskeletal system can fail. Muscles can tear, tendons can become overloaded and degenerate. Bones can accumulate microdamage faster than it can be repaired, leading to stress fractures. These are not examples of fatigue being overridden by willpower. They represent situations in which the protective mechanisms that normally regulate effort are either overwhelmed, ignored, or gradually eroded over time. We'll talk about this in greater detail in the next lecture.